it's my great pleasure to introduce to you Michela Spagnuolo, who is the research director of an institute of almost 100 people. So that's the CNR, that's this Italian very big research institute. That's something we don't have in Austria. These kind of research institutes exist in France and in Italy and so on. And there she's head of the IMATI, that's the Italian name for the Institute for Applied Mathematics and Information Technology. So again, you see here already she's heading a multidisciplinary institute. And Michela has always been interested in geometry, so in the analysis of geometry using mathematical and computational topology tools, and also in the synthesis of geometry. She has also worked on meshes, point clouds, and so on, but I think today she will take us on another journey through virtual and real cities. And with this, please.
Thank you. Thank you, and really thank you for the invitation. I find the program of today really interesting and really fitting also to the topics of the Institute. It is my turn now to be inspiring or confusing, meaning that I wanted to tell you many things. I hope the presentation will not turn out to be not really understandable. So this is the outline. These are the topics on which I would like to bring you along a tour with me in cities. So not so much geometry for the design of new shapes, new assets, but geometry for representing built structures, and in particular aggregates of structures like we find in the city. Then I will go very briefly through not very briefly, actually, it's half of the talk, about one of the strategic projects of the CNR. I will tell you something about, which is called Urban Intelligence. And commenting on this project, I will tell you what the institute I'm directing right now is doing in this context, especially for the geometrical part. I don't use this, but I'm not able. So, first I wanted to tell you something about the CNR. Michael was already presenting something. The CNR is the National Research Council of Italy and is the largest public research organization in Italy. It's funded by the government. And these are the statistics today. So we are a considerable number of researchers working in departments that cover in practice all the fields of research that you can imagine. So today we are 88 institutes at the CNR, which are grouped into 7 thematic departments. The first thing that I want to tell you is that since 2 years we have finally the first woman president of the CNR. This is something that I want to underline also, because also in the audience, the gender balance is something which make me think. But in any case, the president comes from robotics, and so she's also representative of the hard STEM sciences. And the institute, the IMATI Institute, Institute of Applied Mathematics and Information Technology, belongs to the departments of engineering sciences. The institute now is organized in 3 different sites. One is in Genova, one in Pavia, and one in Milano. I was born in Genova, and my working location is now Genova, which is also the largest IMATI site. We are more or less 70 tenured people, plus a considerable number of fellows and associate researchers. So altogether we are 100 people working at IMATI. And you see here the these are recently rephrased, revised research lines of the Institute. So we span from theoretical methods for PDEs and ordinary differential equation, a lot of scientific computing and numerical analysis. This is also quite a tradition of the Institute. Statistics, probability statistics, intelligent information system, Lately, we acquired also a group working on networking and cybersecurity, which is quite interesting, and you will see why. And shape modeling, computer graphics, and visual media, which is the group where I grew up as a researcher. So we were one of the first groups at the CNR working on computer graphics and geometry processing, and I kept working in this domain. IMATI and the shape modeling group is known in the community, not only for geometry processing, but for this idea of linking semantics, knowledge to shape. So we were kind of the first group speaking about semantic 3D object. We were very much interested in understanding the way to represent shapes, but also the way to describe the structure of shapes up to their functional meaning. Semantics as a buzzword, which means what the objects are built for, what is the usage of the object, what is the affordance, how can we use an object to perform actions. So this is kind of a distinctive flavor of the research topic of the shape modeling group. Just to give you a bit of introduction about the cultural background of the talk. So, why the talk points to cities? Cities are really an important part of the worldwide ecosystem. The introduction of the Dean today was really interesting and pointing to sustainability as a key issue, and the management of city, attention to the city, how they behave in terms of impact on the environment, impact on energy consumption is really key. And cities are also one of the points of attention of the Agenda 2030, which I think you all know. This is one of the goals of the sustainable development, how to make cities sustainable and resilient to many of the effects that we see on climate change, and not only, and societal issues like people that are really living in not very good economic and cultural condition. Cities are important. Actually, they cover a small percentage of our world, but they are the cause of the highest consumption of energy. So methods that help us to manage, to control or to modify, to regenerate cities are really, really important. This is something which is not new. The idea of combining technologies with sensor devices and ICT is not new. It was brought to the attention of the community many years ago with the born of the smart city concept. Smart city, which is a way to say how an ecosystem of devices, system, and software service can help mostly monitoring cities, because we have a lot of examples of smart cities around the world, speaking about smart energy delivery, smart mobility, smart whatever. What I can say is that there are not so many examples of a smart city which provide truly a solid decision support system for the public manager, for the decision makers. Still, smart cities are quite organized in silos, thematic silos, mobility, energy, greening, and so on. And the predictive capabilities that are associated to these smart systems are still a bit limited. So here comes the urban intelligence idea, that is the name of a project that was pushed by the department of the CNR on engineering sciences. introducing as a new tool the idea of building sets of digital twins as a key element for the management of the city, but especially for enhancing the predictive capabilities of smart city systems. Digital twins are nothing new. We hear this name mentioned much more frequently in the last years. They were originally introduced in the manufacturing industry to monitor and control better plants. And the first instance of this name dates back to the early 2000s. The digital twin, I think all of you know, is a name that represents a process by which you twin an existing physical object or process with a digital counterpart. And the physical and the digital are kind of aligned, so the state of the physical object or phenomena is aligned through sensors that are capturing its state to the digital associate, the digital twin. What is interesting is that on the digital twin we can make prediction on the evolution of the state of the object. We can make also what if reasoning on the digital twin or on the digital sibling. So we can have copies of the digital twin on which we make changes to see how the situation evolves. We have, of course, a lot of work on digital twins for production. As I said, we start seeing digital twins also for reproducing computationally the behavior of very complex entities or processes like the human being. You remember in the past, in the life science domain, we heard very often the virtual physiological human as a very complex counterpart of the human, and now the digital twin of humans is being addressed by several groups, biological digital twins, and so on and so forth. And the urban intelligence wants to push this idea in the urban management context. So, urban digital twins, what do we mean? Of course, we have to tackle also here with a quite high level of complexity. We have a urban area, a context, a city or a quarter, whatever, and the digital twin should be able to build a digital representation of this environment and be able to align the state of the twin with the state of the city. You can imagine that in this scenario, we are really coping with a highly multidisciplinary problem. We have issues related to the digitization of the built structures of the physical environment. We have to deal with modeling the phenomena, mobility, air quality, pollution distribution, energy consumption, all the layers, the knowledge layers, the life of the city. We have, of course, to have all the sensors possible to make this alignment sustainable and evolving. And we have here another factor of complexity, which is the fact that the cities are coupled with the inhabitants, with the citizens. And this is extremely challenging because human beings are soft issues, not very STEM-like. So in this sense, urban intelligence is very ambitious in its goal of building a platform which is very holistic in terms of trying to address all the facets, the aspects of an urban context, and is trying to push the idea of decision support system, which is built using mathematics or statistics as an engine to search for optimal solution across layers. So if we want to optimize mobility, we have to take care also of the layer related to air pollution. So the optimal solution in one domain needs to take care about the effect, the impacts on the other. And we try to build a system in which these different layers can express their variables, their parameters that are relevant for the optimization and be managed together in a multidisciplinary optimization schema. In this sense, the smart city context concept is coupled with a really heavy scientific computing to turn the smart city into an intelligent city. These are buzzwords, of course, but this is the idea. So the intelligence comes from the digital twin, which encapsulates the physical laws or the data-driven learning of the processes, how they behave, and use this to support decision makers. Integrated and complex knowledge, human in the loop, meaning the citizens should be able to enter in this framework. Multi-level and multi-actor governance, this is of course true, but what is really fascinating me, and this is the reason also why I try to push a bit my colleagues to work on this, is really the highly multidisciplinary nature of this project. We are working with architects, psychologists, civil engineers, people that are working on atmospheric phenomena. So it's really, really challenging and interesting. And it took us, I would say, without joking, 1 year, if not 2, to understand each other and to start setting a common terminology. Even speaking about modeling, this simple word causes lots of misunderstanding problems. So it's really challenging, but really nice. So in this sense, this is a picture which shows you the organization, the very high-level organization of the platform of urban intelligence that we are targeting. So we have several digital twins which are vertical in terms of twinning a specific phenomenon. All these are using or are grounded also on the semantic 3D city model. Very often when you hear about a digital twin of cities, people tend to present you the 3D visualization of the acquisition of the city. This is only one aspect. For us, the digital twin of the city is the whole system. It's not enough to have a very nice, and I will be talking about that, reconstruction of the city itself to be able to say, I have a digital twin of a city. Having said that, as I said, but this is a synthesis, so the urban intelligence is an ecosystem of interconnected digital twins. What is challenging is that each of them requires both static and dynamic data, real-time acquisition, sensor about mobility, spatial occupancy of the public spaces, whatever you can think of. In some cases, they need to be able to provide real-time feedback. We are not close to this result yet, of course. And they have to count on also the possibility to sibling the digital twin on other instances to make decision processes and what-if analysis especially. We started in 2019 to work on this topic, and here are very brief examples of projects at the national level in which we are working on specific practical cases of this idea. The first one is in Matera. Maybe you remember it was the capital of culture in 2019. It's in the south of Italy. It's a wonderful historical small city. And the municipality there was accepting the challenge to work with us on these very first experiments. And they expressed a desire to have 3D city model, of course, and I will show you the geometries there are quite challenging. They wanted to have ways to control mobility, especially pedestrian, because they were flooded of tourists and are flooded of tourists because of the historical value of the city. And they were also very much concerned with environmental issues because the nature, I mean in terms of chemical, of the Sassi. Sassi is the historical center. It's very can be very endangered by the climatic and the situation pollution there. So this was what they wanted to do, and we tried to work on optimization of pedestrian walks based on criteria that tended to minimize optimize the comfort felt during the path, taking into account several parameters like the steepness of the routes and the meteoclimatic condition. Mostly the same criteria for the Catania city. Here we have another ongoing project, again, digital twin of the air, quality of the air, and digital twin of the mobility, plus the 3D city reconstruction. And a very interesting project which started 1 year ago. This is a very big project in the framework of the National Plan for Recovery and Resilience. This is an action that is of technology transfer, but we are doing actually a lot of research on this as well. And here the idea of smart city, urban intelligence is enhanced further with a specific focus on robotics, and how robotics can be embedded in a city as a tool to make to improve well-being. I will tell about this later in a bit more. This is a very big project. We have a funding of 25 million euros only for this specific action. And here we work on accessibility and social inclusion in particular. I will tell you then why geometries are critical. So, speaking now about geometries and the semantic 3D city model. This, as I said before, is actually the basis, is where all the thematic layers connect to the actual urban environment. So a semantic 3D city model has to be very well aligned with the morphology of the city. It should be possibly as rich as the city itself in terms of encapsulating knowledge about what the structures are. It should be connected to all the GIS classical information layers. It should be able to evolve also here with the evolution of the city. In case of any work is done, the 3D city model should portray and evolve with the changes, and should be able to provide the right input to the various vertical digital twin, the thematic digital twins. So in this sense, the very high-level requirements are the ones that are listed. So we have to have a proper representation of the street furniture and structures in the city, but also vegetation, possibly water bodies, whatever you can think of. And these geometric objects need to have a semantic annotation. They need to be explicit in telling what these objects are, and documentation of the changes. Thinking of the different digital twins, thematic digital twins, you can imagine that each of them may require a different digital representation of the reality. If you think about mobility traffic, you probably don't need 3D at all. A 2D map could be sufficient. If you want to think about mobility for pedestrian, then the 3D representation is definitely important. If you want to do any structural analysis on as-built structures, you have to have volumetric representation. If you live in a flat land like some of the cities in the north of Italy, in the Pianura Padana, like Milano, everything is well shaped and well settled on terrain. In Matera, you will see the city is really truly volumetric, meaning that there are immersed areas, substructures under the surface. So every city, every place, and every thematism needs a different geometric representation. Not only, when you think about these kind of platforms, you have to think that the stakeholder, one of the stakeholders are public administrations. They may also have not sufficient expertise, not sufficient funding for doing really extensive surveying of their city to build a 3D model. So we had also to consider how to help public administration to use the data they have and extract as much as possible from their informative resources to be able to enter in this project. Sorry, they're keeping calling me. And in terms of acquisition of the city, we have what is very, very good is that the technology has done really lots of progress. We can acquire cities at the precision that we want. This is an example of the survey that we finished a few months ago in Catania. It's really, we required on a specific, along a specific path, acquisition with in the range of 5 centimeters precision. So it's really an immense source of information. So in terms of tools, we range really from very high precision acquisition, whatever airborne or terrestrial, but we have also very nice, I don't have here a picture, portable laser scanners. And these are, I was really impressed. They can reconstruct point clouds really in a few minutes, and you can do a lot of expeditive surveying on this. We do on the reconstruction aspect not so much work because there is a lot in the literature now, at least not now, not currently, but I will tell you why. And in this phase of the project, we are relying on existing software. There is a lot of work around. There is a huge literature in this field. I wanted to mention actually one of the people here, Michael Wiemer, for this, because one of the first survey in the computer graphics area, at least, was actually produced by Miki. And there is a lot of stuff, even if until now, the process of reconstructing 3D meshes out of this immense amount of data requires still lots of manual process. So there is a lot in the literature. There are many nice tools now, commercial tools, to work with this. There are big companies like the Dassault, the Esri that are investing a lot in this, but still the process of assembling a good 3D model is largely manual. So in this sense, there is, we don't do now research on this, but there is a lot to be done still. What is I wanted to mention is that in the last 10 years, if we take the survey that I mentioned before on urban reconstruction and compare to what's going on in the last years, we see there is a lot of movement from reconstruction for visualization and now reconstruction for using the models in concrete and more practical application, with lots of work and attention in the AI community on the automatic segmentation of point clouds to extract from the point clouds elements of the street furniture or architectural elements. I want to mention, for instance, this, which is a company in the Netherlands, Cyclomedia, which sells now Survey Campaign Plus, a library of furniture that are automatically annotated. Some of the furniture, not all, but some are to be developed with them. They use a lot AI and machine learning, so they remain also, if I understood correctly, their business model, they remain proprietary of the data they acquire, and they do a lot of learning on the data that they acquire and then resell. So data is really a huge potential economical factor. What we have done on 3D city models, these are really very basic geometry processing. This is nothing very innovative from the point of view of research. On the models that we had in Matera, we have done the classical calculation of all the parameters that can be calculated using only geometry, like steepness of the street and sunlight mapping. This is something that I want to tell you a bit more, because you can see that in this case, the morphology is really, really very roughly represented. This was the first example of Matera. Matera didn't have any LiDAR high-resolution acquisition. We received them only last week, but we wanted to proceed with the work. What we did is to use the data that were available, which are DTM, digital terrain model, and digital surface model of a national surveying LiDAR campaign. But the grid size of that acquisition was very coarse, so we had to deal here with 50 meters by 50 meters grid size, which is insufficient for the representation of elements. And what we did in this sense is to exploit as much as possible all the data sources we had. So here you see the DTM built from the LiDAR national surveying campaign. And then we used the OpenStreetMap, which is a fantastic source of information, which is not really accuracy guaranteed, but it's really an interesting source of information. So what we did is to refine this DTM with footprints of buildings and street graphs of OpenStreetMap. And after solving a number of topological inconsistencies between the footprints of buildings, these were mainly overlaying, most of them were overlaying, overlapping, and so on and so forth. What we did, here is an example. We were able to solve some kind of, some form of overlapping and topological inconsistencies up to the resolution level of the grid of the DTM that we had, because otherwise we had no ground to solve these inconsistencies. Once solved, we used these data, so the footprints and the vertices of the footprints and of the streets, to refine a bit. You see in the top here, you see that the meshes is slightly refined, and most important, with the footprints of the building inserted in the triangulation as constraints. So these were part of the surface. We were able to lift the buildings up to the level of the digital surface model that is measured by the LiDAR. So this is a first very rough approximation of the build structure of Matera. And on this we started to work with the other the other services that we had to develop. This I wanted to mention, even if it's not developed in the scope of urban intelligence, but I think it's very important. This is a work of another researcher, a brilliant researcher of my institute, Marco Attene. He has worked a lot on improving robustness of geometric computation. He has reached now, I think, very nice results also on the tetrahedrization, producing tet meshes of constraint to a set of surfaces. And we will be using this to test the reconstruction of meshes also in urban areas. I wanted to mention this because it's really important to help people avoid what at the end of the presentation I will call the technological utopia. What I mean is that you see a very beautiful picture, you think that that picture is the reality. You don't care about precision, accuracy, anything. I've seen many people saying, oh, now I can measure in the digital domain. Well, yes and no. It depends on what is the measure that you want to build. And in improving forcing and accuracy also in geometric computing in this area, I think it's very important if you want to use these technologies released together with civil engineering and really people that need to rely on important geometric accurate geometric models. Another thing that I want to show you is what we did always in this project. In this case, we switched to Catania. This is the 3D mesh of one of the case study area, the one that I showed you before that was scanned. The idea here is to segment in the area the buildings, and associate to the buildings a degree of energy efficiency. This is a work that we are doing with colleagues that are working in this field. These are all civil engineers that have developed their method for classifying buildings according to the expected energy consumption based on a classification of building in canonical types according to the global shape of the building, and they compute this index of energy efficiency according to the surface of the total exposed surface area of the building, the volume of the building, the surface and orientation and slope of the roofs, and the area of the windows. And we have worked with them in this sense. The idea was the following: using the same criteria that I showed you before, using the footprints. We use the footprints of buildings to segment the mesh in buildings blocks. This was quite easy, so we had the point cloud or the mesh, and we projected on the footprint map. So we have the single building. Based on that, with a mixture of ransack criteria, these are quite well known, nothing new. Again, also here, and after transform, we were able to characterize the main parts of the buildings, using also binary space partitioning to decompose the point cloud. Even a single building can be very, very dense of points. So binary space partitioning is a way to cope with the computational complexity of the operation. And thanks to that, we were able to first segment the planar and the primitives that you used. Here was planar, spherical, and cylindrical primitives, and then merge them together to arrive to roofs, facades, and windows. And here is an example of and on this kind of segmentation, this one or this one, we can instantiate the model for energy consumption that I mentioned. And these are two buildings in Catania that were processed with this criteria. Then another example that I wanted to mention is geometry, not only for acquired with point clouds, but also with videos. This is another very interesting experiments that we did, in this case in Genova. We started with videos, images and videos. First, with a learning with a neural net. I don't remember which. I'm not so much interested in the specific architecture. The meaning is that first learning potholes and cracks, and then this system was mounted on a bus in the city of Genova for the automatic detection of potholes and cracks while the bus was going. This was a project specifically with Vodafone as a partner, with a 5G as supporting technology. And I think the results were quite nice. If this will be used in application, I'm not so sure. I really hope so, but it was really a nice experiment. This to say, not only geometry point clouds, but also videos, heterogeneous data can tell us a lot about the shape of the cities we are working. Then here, again, very briefly, one thing. Build structure is not the only element to which we should pay attention when thinking of a 3D city model. Because what is probably, I learned from colleagues, architects and urban planners, what is important is not only what is built, but is what is empty. So the empty spaces in the cities are also really important. These are important because air pollution, noise, meteoclimatic condition actually occur or are located in the empty space, and in this sense, to let our 3D city model interoperate with a thematic digital twin or working on air quality, we had to build a grid of the complement of the built structure in the city. And on this we are experimenting, but this is truly research, novel ways to solve, in this case, Navier-Stokes equations, using grids that are not X-meshes, but polytopic elements. Why polytopic elements? Because we think this could be a way to lower down the computational complexity that Navier-Stokes requires to simulate pollution and diffusion of pollution. And this is an example of what a grid for solving numerically this equation could be. And on this we are working right now. This is truly more research with a PhD that finished last year, is now a contract researcher in our lab. And going towards the end and to the perspective that I want to discuss with you, of course, everything I said should rely and stand on solid basis in terms of standards to be adopted to construct, to store the annotations. And in the project we are relying on the CityGML as a reference standard, which is very, very rich in capability of representing geometry and urban element. It provides already a set of LODs, level of details, which are level of details that resemble the geometric LOD. Footprints, building blocks, but you probably know this standard better than me. And what are the next steps? Where do I see for my group the next duties to be considered, and also some perspective and challenges? So, as I said at the beginning, it's really interesting to say that a 3D model is a combination of at least 3 elements: the morphology, the shape that we want to digitize, the context, the geographical context, and the usage. What is the model used for? Not everything needs the same representation. These are snapshots of Matera. Oops. Can you imagine the complexity of this model? If I want to devise really something automatically to analyze the accessibility to places like this, I need to have a really, really high accuracy. All these streets, and believe me, these are very slippery. I was there many times, so it's really something that could be useful, but it needs a geometric model of high accuracy. These are the constructions that are under the surface. So in this sense, it's really beautiful, the example of Matera, because it's, for the geometric processing community, it's really a challenge per se to devise a model, a geometric model for this. There are lots of construction. You can really walk for many kilometers below with steps, stairs and steep stairs also below. And also you have really nice historical remains with painting that could require also a care on the appearance modeling. So if I want to reason about accessibility, I need a certain quality. But if I want to simply take people around Matera with a virtual visit, I could really skip the geometrical complexity and just texture map the geometry. I try to run fast. This is to say that in the project, what I try to do now is to think about devising a system to represent shapes in which you have one physical entity, which is the city, the quarter that I want to twin, and several digital entities according to the purpose of the entity. And I can skip this. This is not so important. Annotation should be aware that annotation should remain consistent if I change the scale of the representation, because the scale doesn't change the meaning of objects. Tiling and processing. This is something very important. We are speaking about huge point clouds. This poses problem in terms of storage, visualization, of course, and processing. The tiling that we are using now in common systems like Cesium or whatever are mostly oriented towards visualization. What I think would be very useful is to think about partitioning driven by the semantics. If the buildings are the important semantic unit, then I would like to have a partitioning and indexing of my point clouds driven by that concept. This is an example of something that we did in the past for flooding, in which the indexing was driven by the drainage basin of the map of the drainage basins. Then another thing on which I opened a PhD position in the lab is what I call 3D map generalization. It's what we do in cartography. If we change the scale, we change the way we represent entities. The same for 3D. If I change the scale, I would like to be able to represent one building in a way, one quarter in another, really changing the way to represent this model. Quality and accuracy, this I told you before, technological utopia. What we see on screen is not always the truth, and we have to make an effort as computer graphics community at least to be careful to give the right information that is understandable. I'm really close to the end, and here I stole a challenge message given by Thomas Kolbe, who is the founder of the CityGML that we hosted in Genova during the Geometry Summit in July. We should be careful that when we do surveying, we actually survey the exterior part of the buildings. We don't know anything about interior. This is something that we should consider when devising a 3D city model. Maybe it could be nice to think about models in which you have the building, but you also portray somehow the incompleteness where it is incomplete. You could also map this with indoor acquisition to portray them together in a digital 3D model. Then back to the project that I mentioned before, the RAISE project, with a focus on accessibility. The main idea here is that we will bring the human in the loop concretely, so humans will become an element of the urban intelligence. What I mean with that is that we would like to study the shape of the city, taking as a parameter the individual, meaning the individual with the ability, the analysis should be parameterized on the individual. So the accessibility is not the same if I walk on a stair, or if a younger people than me walks, if I'm impaired or not, if I'm fat or slim. So there are many conditions that influence what accessibility means, and in the project we are trying to push this idea a bit further. Ability in sense of sensory motors, also cognitive. What I feel, what I perceive of a space when walking around the city. Concerning accessibility, these are two examples these are snapshots that I took in Rome. Can you imagine that these are, this is in Rome. I was really amazed. I think that this was done exactly for me to show what accessibility could mean. This is a light in the middle of the, I mean, it's impossible. Only if you're very slim and you move. And this is another example of issue for accessibility. If you are on a wheelchair, you cannot really walk here. And last, focus on inclusivement. This is something that we start to work with an architect that is an employee, researcher of the department. And this is a map of the usage of the city space, city public spaces by the people. Here is in Matera. This is where the young people tend to go. This is their ideal area of socialization. What we are now trying to do is to see if there is any correlation between this map, which is a social map for me, and the shape of the environment. If there is any reason to say, okay, these are places where the people feel better because there is more green around, because the shape of the building is more beautiful. Beauty is a very important aspect here. And so this is something that we are really heading forward. So with this last suggestion, I really thank you for your attention.
Thank you. We are a little bit over time, still one or two short questions from the audience. Yes, please.
Thank you for this great presentation. One question which pops up, you mentioned it at the beginning of your talk. Actually, the idea of a digital twin is to have a real interaction with the reality. And you said you don't have any solutions now, but do you have experiments where you have data from the real city, which you bring in the digital model, then you react in the model and bring it back to the reality? Is there any idea where?
There is not really a really worked out idea, but there is one point that I think will be useful to solve this issue. Now there is a lot of work on autonomous driving. So we have potentially a huge number of sensors that acquire data about the physical city. If we could be able to pull this information and match it to the built digital twin, we could have also kind of natural sensors, natural not, but sensors that tells us about how the city is evolving. So this could be, in principle, a way to think about it, beside the fact that you can do surveying to see if things changes, but these are costly. So if you are able to use kinds of input that could arrive from sensors like cars, that could be.
So I have a question regarding the implementation of digital twins. You have shown the enormous complexity of digital twins, not only in terms of geometry, but also semantics, and also various silos, basically stakeholders that digital twins address. So you seem to be very, very advanced in digital part and digital technology, and my question would be, regarding the participation of local governments, also of citizens, because it's basically a cultural change. So every digital twin is only as successful as the stakeholders using it. So if you could maybe give us some insights regarding that, in particular regarding the silo culture that is still present in city governance.
Yeah, this is really one of the key questions. The acceptance of the technologies, at least in Italy, this is the experience I have, I would say is a bit low. What I mean is that they are very fascinating to see what could be done, because they understand the impact, but the local organization is totally not organized, not trained, not able to receive a true input. This is the feeling that we have. Even in the local organization, they still work in silos. They are not used to think that their data could be used or useful for others. For this, we are doing something that it's really a bit boring, but it's useful. A roadshow that was asked us. We are going to visit many municipalities, present this work, try to see if and how they could be engaged in at least some parts. The entry point in the easy way is, the good part is the 3D surveying. If they see the 3D city reconstructed, they are really appealed. So this is a way to catch their attention. But there is a lot to do, and the introductory talk today about training and multidisciplinary training, this is really essential. Also, because if you train new professionals, probably there is an exchange of, an increase of competencies also in these public organizations.
Okay, and one final question over there.
Just a short one. Thank you very much for the very nice presentation. I noticed in one of your slides that you use plenty of open source softwares, from mesh processing to point cloud. Maybe you also plan to release to the public results of your work?
Absolutely, yes. We are now assembling together a modular in which we embed all the services that we have developed so far. So definitely, yes. Working with the public, mostly with the public administration in Italy, we are kind of obliged to use open source.
Okay, so thank you again for the great presentation.